Welcome, everybody. Welcome to the University of York's Physics Winter Webinar Series. This is the latest in our series, and it's really great to have you all here. I'd like to start with a few technical notes to make sure everything's on the same page. First of all, my name is Dr. Chris Murphy. I'm one of the senior admissions tutors in the Department of Physics here at the University of York. I'm also a laser plasma physicist, which will become relevant in a second, and I'm fortunate enough to get to host these speakers, some really interesting speakers. A few technical notes before we start. If you are watching live, you can ask questions using the Q&A button on your screen. It's usually at the bottom. It might be at the top, depending on what kind of device you're watching on. And that's available throughout the event, so you can ask questions at any time. If they're technical questions, then we'll probably try and answer them in the chat and then Q&A. Otherwise, I'll be posting those questions to our speaker at the end during a Q&A session. If you have got any technical issues, such as loss of Wi-Fi, you can always rejoin the event using the original link that you had. And remember, this event is being recorded. So if you missed any of it, or if you just like to watch it again and sort of pick up some of those details that you missed first time round, you can always watch it again. The subtitles are available in the event by clicking the CC Live Transcript button, which is probably again at the bottom of your screen. And you can use that button to switch those subtitles on and off. So a little bit about our winter webinar series for those of you who are joining us for the first time. The idea is to bring you some of the most exciting cutting edge research that's being done at the university to scientists of all ages. So whoever you are and wherever you come from, hopefully this will appeal to your interest in science. The event takes place on the second Wednesday of each month, and we'll have a speaker who's working, an internationally renowned speaker who's working at the forefront of their own discipline. Upcoming talks in the series after this evening's, we'll have Mikhail Bashkinov speaking in February. He'll talk about some of the advances in our understanding of the early universe in terms of subatomic particles known as quarks, and in particular strange quarks. In March, we'll have Professor Marco Luca-Marini speaking about some exciting applications of quantum mechanics, so how his research uses quantum technologies in order to advance consumer products, things like cutting-edge phones that we might see coming into our pockets and into our hands in the future years. All of these different topics that we have discussed in this seminar series linked to the physics MOOC that we offer. This is an online course that we offer through FutureLearn that will allow you to find out a bit more about the topics and actually learn some more of the details yourself. A link to register for that is just been posted in the chat and will be available to you in the video description for those of you watching later on YouTube. So, I'm now going to, it's a great pleasure and with some pride, I get to introduce our speaker for this evening, who is Emma Hume. Emma is a graduate of the University of York. She completed her master's here a few years ago. She then proceeded to a PhD program in physics at York, actually being based here as a member of the York Plasma Institute. She currently organises a podcast on fusion energy, which is called A Glass of Seawater. This is something which we'll try and get a link to that as well, popped in the chat so that you can join it. If you're interested in fusion energy and some of the topics, some of the issues raised in this evening's talk, you might like to join and sign up to that. But as well as that, of course, she's doing a PhD, where she's completing her doctoral work on experimental laser plasma physics with an eye on fusion, that ultimate goal of clean nuclear energy for the future, where she's supervised by the excellent Dr. Kate Lancaster here at the University of York. So tonight she's going to talk a little bit about creating stars using high power lasers. I won't steal any of her thunder by going through any of the details. I'm sure she'll be able to take through all of that herself. Just to let you know that after the presentation, there'll be questions from the audience, from you. So please do submit questions throughout this evening's event via the Q&A button at the bottom of the screen. And I'll come back on at the end and put some of those questions to Emma. And hopefully we'll manage to get through most of the questions that you have. So without further ado, we have Emma Hume. So I will now switch off and invite Emma to share her talk and get started. And over to you, Emma.
Fantastic. All right. Well, thank you very much for that introduction, Chris. It's very nice to be working with you virtually again. So today I've got the great pleasure of joining you as part of our winter webinar series to speak to you about the work that we're actually carrying out here in York and at other facilities across the world, looking at using these really high power lasers in order to create and understand stars within a lab. So you've hopefully probably either seen, heard of, or used a laser at some point within your daily life. So you probably have some kind of idea of what a laser is already. So here I've got a few examples of where you might have seen one knocking about. So a couple of examples would be in barcode scanners that you do maybe at the supermarket, and fiber optic communications, fiber optic cables use monochromatic or laser light in order to pass on information. Could have seen it in a bit more jazzy aspect, maybe as a festival or a music show as part of a laser light show. We also have applications in areas such as like in DVD players and Blu-rays. They all use lasers in order to actually read discs. DVD players use a red laser light and Blu-rays use a blue laser light. Well, I think actually technically it's violet, but we'll call it blue, which is why it's called a Blu-ray device. You may have also seen lasers in sci-fi. It's quite, because it looks really cool, it's quite good sci-fi fodder. So we have seen lasers in places such like Star Wars, we've got our droid laser guns there. And we also quite often see them as kind of like security devices as shown in, I think it's a snapshot from Ocean's 12. So it's quite common and they do look very, very cool. But they do also have a bit of use to us, which hopefully I'll be able to convey to you during this webinar today. So typically, when we're looking at lasers that you use day to day, they are relatively low power. So taking the example of a laser pointer pen, these laser pointer pens have powers of onto the order of milliwatts. So for this example, it would be like 0.005 watts. So even at the milliwatt power, you can appreciate that a laser pointer is still quite bright, right? There is still quite a lot of power being involved in that, brightness being involved in that. You know, they're saying you shouldn't exactly point them in your eyes because you can cause damage. They do still quite pack a bit of a punch even at milliwatts. So here at York and other universities as well, we are, however, interested in using even more powerful lasers in order to explore really extreme physics. But how much high power are we talking about? Well, to take the example of one of the lasers down in Oxford, that laser is capable of delivering powers to the order of petawatts, so one with 15 zeros at the end of it. So we have something that is substantially more powerful than you'd get from a laser pointer pen, whack it right up to something that's millions and billions of times more powerful. So we can create some really, really incredible stuff there. But the question is, how do we take the principles of how a laser pointer pen works and scale it up that much so that we're able to create these super, super powerful lasers? How on earth do we get from a laser pointer pen to something that's like millions of times more powerful? So to start things off, I want to spend the first half of this webinar basically explaining a little bit more about the concept of these high power lasers and exactly where do they come from, how on earth do we achieve these. So we'll start with a bit more of a fundamental question of what actually is a laser. Just thinking about it at first glance, you could say that maybe, oh, a laser light is just like a really intense beam of light, which kind of is, but it's a little bit more complicated than that, because if you use that argument, well, technically, a beam of light could be like a torchlight or like the beacon from Batman or something, any bright beam of light. Is that a laser? Not quite. There's something a little bit different, a little bit special about the properties of laser light that makes it a laser. So one of the key properties that defines a laser as opposed to the light source from, say, a torch or a bulb is this property called coherence. So we know that light travels as a wave, it travels as an electromagnetic wave, and this wave will have associated with it a wavelength, which defines kind of like how short all these peaks and troughs are. If you have a light source from, say, like a white light or a torch or a light bulb, you will emit light with lots of different wavelengths. So we won't just have one single wavelength, you'll have it with lots of different wavelengths and lots of different colours. Additionally, you'll find that each wave might have different kind of amplitudes, or some waves will be stronger than others. And additionally, they'll be spaced out spatially. So you'll find that'll be quite a large divergence. So it won't necessarily be going in a super straight line. It will be spreading out when you actually fire it as well. Laser light is different in that it can be defined as being coherent. So it will emit light with the wavelength and the frequency of all of its waves that make up that light is identical. So it's all the same color, basically. It's monochromatic. And it'll all be in phase with each other, which means that the peaks and the troughs of our waves all kind of coincide with each other, so they're coherent. And this has the benefit of basically meaning that our beam can be really kind of neatly focused, right? So it means you can travel much further than, say, like if you're trying to shoot a torch at something 10 meters away, you wouldn't see the torch at the other wall, but if you shoot at a laser pen, you'd still be able to see it. And that's due to this coherent nature of the laser light. So in terms of how we actually produce a laser, this is really critical in terms of understanding how we actually produce our high power lasers as well. So how do we get a laser to work? Where does it come from? Well, in terms of understanding how a laser works, you can actually technically look at the word laser itself, because the word laser is an acronym which explains how it works. So laser stands for light amplification by the stimulated emission of radiation. Now, I don't expect you to understand that purely just from reading that. I am going to delve into it in two separate parts to try and explain that a little bit further and help show you how a laser works. So the first part is light amplification. So essentially, a laser is working by taking some seed amount of light, so a small amount of light, and making it more amplified, giving it more energy, okay? So the way of thinking about this is our light that will be forming up the laser light can be described in terms of photons, which are essentially like little packets of light. So our little waves are going to travel in these little packets. The energy of each photon is related to AHF, so the frequency of the light. So each of these photons is going to have the same amount of energy because it's going to have the same wavelength, the same frequency. So in order for a laser to work, in terms of amplifying it, we want to give it more energy. The way we do that is by producing more photons. So the more photons that we've got within our kind of laser pulse, the more energy it's going to have. So the whole point of it is taking a little bit of light and then creating more photons out of it to give it more energy. And the way that we do that is through this process called stimulated emission. Now, it's not important for this talk to understand exactly how it works, but the main principle to take away from it is it's essentially like, it's a process that happens to the electrons in the material. So you'll have a photon of a particular wavelength, a different color coming in. It will then essentially stimulate or force some of the electrons within that material to emit another photon. So it'll emit some more radiation. And the key thing about this is that this additional radiation that's emitted, this additional photon, is going to have the same color, it's going to be traveling in phase, and you essentially have boosted the amount of photons that you've got. So in this way, this process can help you produce more photons from one seed photon, so on and so forth. It should be noted that stimulated emission is not the only process that happens to the electrons in the material. So you can have things like absorption. So you'll have your photons just being absorbed by the material. You get normal emission where it'll just be emitted in all directions and it won't necessarily be going in the right direction. That can reduce the number of photons you actually get out. So it's kind of a bit counterproductive, which means that you do have to choose your medium quite carefully. So there's only certain materials that will actually work in terms of kind of having like a net output of more photons compared to others. So in terms of how this works in practice, at lower powers, we can kind of stimulate it to work continuously. So you start off with our little block, which would just be like what we call the gain medium. So that's the material where all of our kind of amplification, our additional photon creation is going to happen. So you'll put in a little bit of seed light, a little photon, we'll get it to put in that material. It'll then produce another photon, and those photons will then produce more photons. We then make use of mirrors around this gain medium to make sure that all of these photons, or the majority of them, will stay within the medium for as long as possible. So instead of just traveling back out, it'll bounce back in, being able to cause kind of more stimulated emission events, and then some more, and then it keeps bouncing about. So eventually you get to a point where you've just got photons continuously bounding around, got some more being created. And the key thing in terms of actually getting the laser light from this is the fact that one of our mirrors, as you can see, will only be 99.9% reflective, so it won't be 100% reflective. So once we have a high enough number of photons bouncing about within our cavity, you'd essentially start to get a decent amount coming up the other end as well. Now, the photon creation does eventually reach a steady state, so you don't just get a continuously increasing number of photons forever and ever. It does kind of start to even out a little bit, And so you end up with this continuous beam of light coming at the end of our laser. So in this way, we can use this principle to run lower power lasers forever. So you can just leave a laser pen on for as long as you want, and that's absolutely fine, right? Now, when we start to look at higher powers, we start to run into a little bit of an issue. So obviously we want to get high power. So it means we want to start packing in as much energy as possible, as power is energy per unit time. So the more energy we have, the higher powers that we've got. However, there is another property of laser light called fluence, which is the amount of energy you have per area. So how much is packed into a small space. And as we know, laser light is quite narrow, it's quite focused, it'll form a tiny little spot. So it's quite easy at high powers to therefore get a really high fluence as well. This ends up having a really big issue in terms of the laser optics. So if you try and pass a really high fluence beam through some of our optics, through a lens, for example, or our amplifier medium, you'll find that it actually causes damage to the material itself. So it can cause like cracks and fractures in the middle of it. It can kind of damage how well focused the beam is, so you don't get quite as good a laser out the other end, and it causes quite a few issues. And obviously, well, not obviously, but these amplifier mediums can be quite expensive, and it's going to be really impractical if every time we want to fire our laser, it breaks and we have to replace it every single time. It's not practical, so we need to use a slightly different approach to make sure that we're generating our laser light, but not breaking all our optics every single time we press fire. So one of the solutions that we can use is to, instead of just having kind of one amplifier and one kind of block of material with mirrors on the other side to continuously amplify the same seed, what we can instead do is use several amplifiers essentially in a row and pass through the laser light through all of those to amplify it in stages. So this is an example of the amplifier setup that's used at the Vulcan laser down in Oxford. So we can see we've got like 7 different amplifiers used. So you start off with a rod amplifier, which has got a smaller diameter of around 2 centimeters. You'll pass your initial bit of light through there. You'll then pass it through another amplifier with a bit of a bigger area, and then a bigger area and bigger area. Each time also increasing the size of the laser beam as well. So our fluence, so the energy per area, will decrease and not get so high. You then end up passing it through these final set of optics, which are these disc amplifiers. It turns out it's quite difficult to create rods with that diameter, so you have to use flat discs instead, which have been increased to a diameter of about 21 centimeters. So they can be quite big amplifiers at the end. And then once we've got our amplified laser beam, so we've got lots of photons now after it's passed through all of these different amplifiers, we can then focus it down to carry out some exciting physics at the end. So just to kind of show a little bit the scale of these high power lasers and what we actually need to do to create so much light. This is a schematic of the Vulcan laser setup that's based down in Oxford, just to show the scale of it. So this is a facility that only has one laser. So we think, I keep referring back to the laser pen, but it's a good example, right? A laser pen is only probably about this big. To create our high power lasers, we need a facility to the order of, 50 meters across by 75 meters. So this is for one laser beam, just the one. It's absolutely incredible. So there's not just the amplifier mediums in there. Obviously, we're going to have all of our crystals to produce all of our laser light. There are a lot more optics in there. So you've got things like optics to make sure that the wavelength of the light that you are creating is correct and really high fidelity. Also ones to kind of focus it down and make sure it's the right shape temporally. So it's not just amplifiers, but there are a bunch of optics there that spans across rooms and rooms. So it's a ridiculously large scale. So you end up having it travel through all of these different rooms, getting amplified, getting more energy as it passes through. And at the end, we focus it down to this target chamber down here. And as you can see, this is what the inside of the target chamber looks like. This shows someone actually setting up a target. So this is what we're going to be firing our laser at. Is you can just about make out the target there. So you shoot it with this huge beam, focus down onto an incredibly small target. So we have ridiculously high powers and very, very small targets. So by doing this, provides us with the ability to create really hot and dense conditions. So in my area of physics, we're interested in looking at something called a high intensity regime. So it means we've got a really high power lasers, but in a really, really small volume area. Yeah. So once we've taken a high power laser, once it's been amplified through all those amplifiers, we focus it down onto a really tight focal spot, which is the order of about 10 microns. So to put that into perspective, the width of a human hair is about 50 microns. So we're focusing all down to a tiny, tiny spot that you probably would barely be able to see with your naked eye. So we get down to really, really ridiculously small conditions. For us, that makes some really interesting physics because you essentially are creating something called, we are accessing something called the high energy density regime. So we're packing loads and loads of energy into a really, really small volume. And that basically means that we can start to access some really extreme material conditions. So in some of these experiments, we've been able to reach some ridiculously high temperatures. So we've been able to create material with temperatures up to, say, 10 million degrees Celsius. And we've also been able to squash this material down and compress it to densities that are 100 times more dense than, say, a metal block. So you start to access some really hot and some really dense conditions. But why do we go to all this trouble? So it seems like quite a lot of faff to create this ridiculously high power laser. It's quite a lot of effort to be able to focus it down onto these tiny, tiny targets. What is the point? Why do we want to do that? Why do we care about high energy density physics? So this is where the motivation comes into it. And the key things that we want to explore, some of the key things we want to explore are laboratory astrophysics and applications in fusion energy. So lab astro is the perfect candidate for, or astrophysics is the perfect candidate for high energy density. So you can imagine in stars, supernova, planetary cores, they're all very warm or high energy density. And we also have application in fusion energy, which I will touch upon in the second half. So to start off with the motivations, I wanted to take some time to basically talk you through some of these experiments that have been carried out to investigate laboratory astrophysics, just to give you a bit of a taste of the breadth of astrophysical phenomena that we can actually explore with these high power lasers. So starting off with an example of a brown dwarf. So brown dwarfs are these kind of harshly described like failed planets. So they basically bridge the gap between a low mass star and a planet. So one kind of open question, or a question that's still not completely answered, is what's so different about the material in the kind of baby brown dwarf that means that it doesn't turn into a planet? You know, what's different about that material that means it's not quite sufficient to turn into a planet? And one way to try and explore this is to carry out experiments using our lab, using the high power lasers in the lab, to try and recreate the conditions of a brown dwarf and see exactly what's going on with this material, and see if measuring the properties of that material can give us a bit of an insight into what's going on inside there. So one of these experiments, you can measure some pretty cool things. So this experiment in particular, it used a high power laser to irradiate a plastic target, and it was used to heat it up and compress it to temperatures and densities that were similar to what you'd find inside a brown dwarf. So you're creating the conditions of a brown dwarf in our lab. What you can then do is measure things like the X-rays that are emitted from it, so our X-ray emission that is radiated from it. And this can give you a bit of a clue in terms of what's actually going on inside the material. How are the electrons in there behaving, and what can that tell us? So I think the outcome from this paper was that it was able to measure the resistivity of the material, so how much resistance it had when you passed a current through it. And it showed that actually what we thought the resistivity would be inside a brown dwarf was a little bit different to what was measured or what was inferred. So by carrying out this experiment in the laboratory, it's enabled us to update our theory and our understanding of how the material inside a brown dwarf behaves. So that's pretty cool. Because obviously it's quite hard to probe inside the core of a planet by hand, so at least we can do it in our lab instead. So we have another application in terms of planets, in terms of how planets are actually formed as well, so higher density ones. So for terrestrial planets like Earth, the makeup of a planetary core is basically that you have kind of like this blob, this metallic core in the middle, that is surrounded by a mantle, so like another kind of layer of different material. But it's quite an interesting question in terms of looking at how exactly these planets are formed. So how is this kind of structure actually formed in the middle? So looking at early times of a planet's lifetime, all of this material is kind of like jumbled up. So you have the mantle material, and then you also have like the metallic blobs that are going to eventually make up our core, kind of like dotted in around there. Over time, these blobs will end up kind of rising or moving up to the surface or up to the top layer of the mantle. But then the question is, obviously, these metallic blobs are meant to form the core, right? They should be right in the middle. So how do they get from the edge into the middle? And it turns out that part of the question, or part of the answer, it comes from something called the Rayleigh-Taylor instability, which is an instability that occurs when you have a higher density fluid sitting on top of a lower density fluid under the influence of gravity. So we know that F equals mg, so we're going to have a greater force on the higher density fluid sitting on the top, and that causes it to essentially be dragged down and form these kind of like fingers of material blending into our lower density material at the bottom. So in the context of the planetary cores, you would imagine that this kind of red liquid in the glass would be representative of our metallic core material, and the clear liquid would be part of like the mantle material. So we can see it kind of like steeping down. But what we don't know is how quickly this effect takes place inside a planet. So it's, again, because it's early times, it's already happened, right? We need to be able to kind of measure it and look at it after the fact. So again, we can use experiments using our high power lasers to try and replicate a little bit what this material would look like and how quickly our high density material will be dragged down through our lower density material. So for this, we can use, again, a high power laser, and we can fire it at a sample that's made of 2 layers. So I'll have a high density layer on the top and a lower density on the bottom. And the point of doing this is that it essentially launches a shock through our material. So we're putting so much energy into the sample over a really short period of time that it essentially launches a shockwave through it, and that accelerates it. So under this acceleration, it means that our sample is experiencing like an artificially high gravity, because gravity is essentially, it accelerates us down. It's an acceleration force. So we kind of force it to undergo this kind of like fake gravity, which would be similar to what kind of gravity you'd experience inside the planetary core. So this has been done in an experiment, and they've been able to achieve kind of like fake or experimental gravities of the order of 10 to the 13. So again, that's one with 13 zeros over it. And from comparison, the gravity that me and you are experiencing right now is to the order of about 10 meters per second squared. So again, we're getting stuff that's ridiculously higher that we've been able to create in a lab to try and replicate how a planet behaves, but within a laboratory. And from this, we're able to measure exactly how fast this Rayleigh-Taylor instability kind of grows, how quickly our core material gets dragged through, and how much of a part that has to play in terms of planetary core evolution. So in terms of stars as well, we can also use laboratory astrophysics experiments to understand supernovas. So a supernova is essentially an explosion of a dying star, and it kind of like will blow out and create like a massive kind of blast shockwave, leaving behind lots of material that we call a supernova remnant. Now we can take pictures of these supernovae, so we can take pictures of it using kind of like X-ray and radio images. And images were taken of this supernova in particular. So this is Cassiopeia A. And something that quite interested scientists was that the magnetic fields that they were able to infer from these images were found to be 100 times higher than any of the other magnetic fields around it. So you kind of found these little localized, really high, like really strong magnetic fields chilling about in the supernova. So the question was, where did this kind of magnetic field amplification come from? What is it within this supernova material, or what happened with the supernova shock in order to cause such high magnetic fields to be generated? So again, we can use an experiment using our high power lasers to investigate exactly what was going on for this particular supernova. So in this experiment, a laser was used to heat up a carbon rod. So when it fired on that carbon rod, the whole thing basically kind of gets blown apart and you form a shockwave. So the whole thing will end up blasting out and forming a shockwave, which would be very similar to a blast wave, similar to what would be inside a supernova. So you're essentially making a mini supernova in our lab. What these physicists then did was to then explore what you can do to this produced shock, the supernova, in order to try and induce greater magnetic fields. So they just produced kind of like a basic shock, so just heated up the rod, created a shock, and measured the magnetic field from that. They then also carried out a slightly different experiment where they created the shock, but then made it pass through a plastic grid, which basically had the effect of kind of like chopping up our shock and causing it to be something called turbulent, bit messy, and then measured the magnetic field afterwards, so measuring the magnetic field in this turbulent shock. And they found that putting this plastic grid in place actually made the magnetic field values loads bigger. It amplified it up. So what this demonstrated for these physicists was that actually what was probably happening inside the supernova that was imaged was that our shock was passing through kind of like clumps of material that was already there in the sky. And once it kind of passed through all these like clumps, it was messing up the shock and it was contributing to this increase in magnetic field. So by studying it in the lab, we've been able to understand this kind of like fundamental question of what was going on. So I've got one final example in terms of laboratory astrophysics, and this one is a slightly clickbaity title, but looking at diamond rain on Neptune. So Neptune and Uranus are both classified as icy planets, where the ice refers to the fact that it contains light elements containing hydrogen, so materials such as like water, ammonia, and methane, which we'll touch on again later. Now, the atmosphere and the conditions on Neptune are quite extreme, so it can reach temperatures of tens of thousands of degrees Celsius, and it also has pressures of around 10 million bar. Again, for comparison to us on Earth, the average temperature of the atmosphere on Earth is about 20 degrees Celsius, although I'm fairly sure it's not 20 degrees outside now. And the pressure that we experience is around 1 bar. So we reach temperatures that are substantially higher and pressures that are literally like 10 million times higher. So some really extreme conditions there. And we really want to explore how our kind of like icy materials inside this, our icy planets like Neptune, behave, what they actually do under these really intense conditions. So the material in particular that we're quite interested in is looking at how methane behaves in the atmosphere. So methane is made up of carbon with 4 hydrogens. And at these kind of high pressures and these high temperatures, what you'll find is that the carbon and the hydrogens will split up, they'll dissociate. So you'll have carbon lying about basically, which can do some interesting things under high pressure. So again, experiments carried out in the lab to model how carbon behaves under different pressures. So what you can do is take a sample of your carbon, or if you want to do it for water or any other different material, you can fire a laser at it, and again, it launches this shock into it, which compresses it down. Well, obviously, if you squash things down, there's going to be more pressure, right? So you can use these kind of laser irradiated samples to reach different pressures, and you can measure what the pressure is, you can measure the temperature. So you can do this and access lots of different pressures and lots of different temperatures. So what you can then do is plot our measurements on a graph. So this kind of line highlighted in yellow shows the measurements of the material that is present inside Neptune, or would be present inside Neptune. So as you can see, for each pressure, there's only kind of like one temperature that material could potentially have. And that's because these materials follow something called an equation of state, which basically means that at a given density, if a material has a certain pressure, it must have a certain temperature. So our pressures and temperature values always have to come as a pair. So it always has to come together, and it's always going to follow that line for a given density. So it means that any material in Neptune will follow that line. So if it's got a pressure of 2 megabar, then it's going to have a temperature of around 6,000 Kelvin, basically. What this has been plotted on top of is something called a phase diagram. which basically describes what state our carbon is going to be under these different conditions. So you can see we've got it at kind of like higher temperatures, it will form a metallic liquid. At lower temperatures, it'll form a metallic solid. But interestingly, down here, if we have lower pressures and slightly lower temperatures, it will form diamond. So this is where we come to our diamond rain part, because as you can see, there is a portion of that line of material properties that the ice material can hold. A portion of that does lie within the diamond state. And these conditions are relevant to the conditions that would be at the top of the atmosphere. So kind of like further away from the core, that will have material, that will have pressures kind of like down here in lower temperatures around 2000 degrees. So what you'll find is actually at the top of the atmosphere, according to this diagram, you will have diamonds being formed essentially in the sky, and Neptune, which will technically then fall down. So you then get kind of like diamond precipitation almost, or a diamond rain, which is really, really cool and kind of an unexpected outcome of some of these experiments. So I've shown a few examples of how we can use kind of like laser-driven experiments to understand and explore different astrophysical phenomena. So how we can use it to understand supernova and planetary cores and some stars. But what we can also do is use this research to kind of utilize some of this kind of power for ourselves. So this kind of second half is going to be looking at another slightly different application where we're using our high power lasers to try and essentially produce mini suns or mini stars on Earth that we can use for power. So you can use it for fusion power. So stars like our sun create energy using the process of nuclear fusion. So don't be put off by the word nuclear. The word nuclear here basically means that it's got something to do with the nucleus of an atom, right? So it's the fusion of two nuclei. So the way that it works is like you'll have two light elements. So in here we have D, which is deuterium, and T, which is tritium, and they are both kind of different types of hydrogen. When they're at really high kind of energies, which is really high temperatures, like what you'd find inside the core of the sun, you'll find that they've got so much energy that they'll be bouncing around, they'll bash into each other, and they will fuse together. And this fusion process actually causes energy to be emitted. And that's how the sun is powered and how other stars are powered as well. So by smashing these nuclei together, you can create energy out of that, which is a really, really cool idea. So in terms of kind of our fuel, it's quite easy for us to get some of the materials. So deuterium, which is the lighter one, we can get quite readily from seawater. It's light on heavy water. And the tritium we can make using kind of larger reactors. So we can use it. So we can get it from reactors like this is a picture of the CANDU reactor that's in Canada. So we can produce this fuel on Earth as well. So we are trying at the moment to try and actually achieve this fusion for ourselves. So it would be really cool if we could actually do this fusion ourselves on Earth and try and kind of create some energy from this readily available fuel, because obviously at the moment climate change and the idea of trying to use more renewable energy is a really, really hot topic at the moment. This could potentially be in part of the answer to that, right? So fusion energy, if we could get it to work, would be really, really cool. One way that we can try and actually get this fusion to occur here on Earth and actually get fusion to happen is to use our high power lasers. So you'll start off with a blob of fuel. So that'll be made up with our different types of hydrogen. And you actually contain that within a shell that's made out of plastic. So you then use multiple different lasers and fire it around this kind of like pellet of fuel onto the plastic shell. And this laser interaction will heat the plastic shell up and cause it to explode out. Now, from Newton's first law, we know that every force has an equal and opposite reaction force. So by blowing our plastic shell out, you then actually cause a reactionary force inwards that will compress all of our fuel pellet and make it down further and further. So by compressing it, we'll increase the pressure, we'll increase the temperature, and we're essentially trying to cause a mini sun to be formed that will then start to kind of fuse the fuel together. It's at a high enough temperature and a high enough pressure in order to start sticking together and then start spitting some energy out, which would be fantastic. So we are actually doing this on Earth at the moment. In particular, one of the kind of like front runners at the moment, I would say, is the National Ignition Facility. So NIF, the facility is based in California, and it holds the largest laser in the world. So this laser has got more energy than any other laser that we have presently. The way it works is it basically will produce this really high power laser and will produce 192 separate beams. So when I said you fire quite a few around a pellet, this one will produce 192. That will all coincide around this tiny, tiny fuel capsule, which I'll show on the next slide to give you an idea of how small all of these beams that are going on to. So you may have actually heard of NIF already. It is probably the most famous inertial confinement fusion facility that we have. Here we can see this is a still from, I think it was a Star Trek movie, and they can actually use it because it does look pretty sci-fi, but this is actually a real facility, and it is actually carrying out fusion experiments now. So on NIF, the way that our fuel capsules, our little pellets are set up is slightly different to the diagram that I just showed. So we'll hold our little fuel pellet inside a little gold canister, which is something known as a horon. So the reason why we do this is because firing these 192 lasers around the capsule is all well and good, but it has to be super, super precise. And if you misplace even one of them a little bit more, it means that you're not going to compress your fuel completely symmetrically. So you're not going to get quite as good fusion coming out, and it's not going to be the most efficient shot that you can have. So what you can instead do is cheat slightly and fire the lasers at this horon instead. So once you've fired it at your gold material, it will essentially produce a bath of X-rays instead. So you will have your fuel capsule, instead of being hit by the lasers directly, it'll be hit by like a lot more X-rays that are being produced from our lasers interacting with our gold capsule. And that can help produce kind of like a more efficient, more spherical compression. Should be noted in terms of the scales as well. On this image here, the horon is about 1 centimetre tall, and our fuel capsule is only about the size of a peppercorn. So we're talking about kind of focusing down 192 separate lasers onto something that is essentially the size of a peppercorn is, as you can imagine, it's a very precise job. It's not easy to do, and it's something that NIF has been working on for the past 10 years or so to try and achieve. So I wanted to end on a kind of a bit of a positive note in terms of the process of inertial confinement fusion at the moment. So actually, fusion is difficult to kind of get to work and get to happen on Earth, but we are actually making it happen. And recently, we had a really exciting development in that back in August, we had the most energy out of a laser shot ever on this ICF capsule. So we managed to get out 1.3 megajoules of energy when the amount of energy that was put in was about 1.8 megajoules. So we got 70% of our energy back, which maybe doesn't sound so good, but for us, that's actually a really, really huge milestone. So at the moment, as I say, we can actually get fusion to happen, but what we're kind of struggling with a little bit at the moment is trying to make it efficient, because we really want to use fusion as a kind of energy production source, right? But at the moment, we have to put in so much energy, the energy out isn't enough to balance it out. We're putting more energy in than we're getting out, so it's obviously not a very good energy production source at the moment. But this record-breaking development a few months ago has been a significant step in terms of getting closer to ignition and getting closer to that kind of like break even and starting to actually gain some energy out of there. It's tantalizingly close. It's very exciting to be part of the ICF community right now and to see some of the steps that they're taking. So there's a few kind of ideas in terms of what we can do to increase the energy that we get out, and hopefully in the next few years we'll be able to actually achieve some kind of like viable energy output through these endeavours. So I know if you're familiar with fusion at all or have heard of fusion at all, you've probably seen the tokamaks before, which is the kind of magnetically confined fusion instead. So it's also worth having a look at this inertially confined fusion as well, because I feel like there's going to be some pretty big additional breakthroughs with that in the future as well. So with that, I think I'll bring my content to a close. That's everything that I wanted to cover today. Hopefully that was of interest to you in terms of learning exactly what a high power laser is, the efforts we have to go to actually create them. And you've had a bit of a taste of the kind of research that we can actually carry out with them in terms of exploring astrophysics or stars and planetary cores, and also how we can use it to hopefully produce fusion energy in the future. So with that, I wanted to thank you very much for your attention and for listening, and I'm happy to answer any questions that there are.
Thanks so much for that, Emma. That was really interesting and really exciting. I really like the way you sort of brought in all the different aspects of astrophysics, as well as the sort of more, I guess, high-profile fusion aspects of it. We do have lots of questions, quite a lot of them relating to lasers. So I might just have a quick, almost yes and no to some of these. Laser light is in phase, but isn't it also polarized? From Pauline.
It is polarized. Is it polarized? It is polarized, yep. So the whole point of coherence is it does have to kind of behave all the same, right? So it will be polarized as well. So yes, in phase and also polarized.
And it's a chain exponential reaction. I think that's in reference to this idea that, do you get more and more photons, and does that pattern, is it an exponential growth, and does it continue indefinitely? I guess that. Maybe.
Yeah, so in terms of our lower power ones, obviously you mentioned the fact that you kind of have your mirrors on either side. So in theory, your photons are bouncing around forever. However, what we found is that, yes, it grows very rapidly at the start. So you do get kind of almost exponential at the start. But then you start to have other processes kicking in. So stimulated emission was one of them, but you have other processes like absorption and other types of emission that can occur that will reduce down the number of useful photons that we get out almost. So you start to reach a bit of a steady state. So initially the increase is really, really quick, and then it does kind of like level out. So we get something continuous. So it means that eventually, at the start you'll get it ramping up, but at the end it will level out till you start to get a constant number of photons being produced.
I think that also answers the question that Gabriel had, which is what's the difference between stimulated emission and absorption and re-emission of photons in the laser medium. I guess that's about whether it's coherent and driven or whether it's just spontaneous, I guess. Okay.
Exactly, yeah. It's that spontaneous thing, because an electron can either do it by itself and just kind of be excited and then just emit a photon by itself, or you have the stimulated version where another photon comes in and essentially forces it to spit some energy out.
Great. A few other questions. Are lasers always visible, or are there gamma ray lasers?
Oh, so first part, gamma. Lasers are not always visible because we can produce lasers of lots of different wavelengths. So you can have them in the infrared or the X-ray regime. So they don't have to be visible, because technically, yes, it produces light, but not all light is visible light, right? We have a whole spectrum, and it can be part of any part of that spectrum. Well, depending on the material you use, obviously. So I know that you definitely have like infrared and gamma ray, but I don't. Not infrared and gamma ray, sorry, infrared and X-ray, but I don't know about gamma ray. I'm not sure if gamma ray ones exist. I'm not sure.
I would say it's probably dependent on your definition of gamma ray to some extent. And even X-ray lasers, they operate in a different regime. That tends to be a free electron laser, which is not really the same process. It's got the same name, but only because the physics internally is a bit similar, I guess. And how did you decide what wavelength to use in your lasers?
So part
do you choose at all, I guess?
Well, that's the thing. So part of it is kind of taken out your hands a little bit. So the energies and the wavelength of the light that's emitted is kind of dependent on the properties of the material that you're using to produce your laser. So as we're talking about, we've got lots of different atomic processes or processes that can happen to electrons in a material. And they all have quite like distinct different energies at which these processes can happen. And as we know, the energies are related to your frequency and to your wavelength. So you kind of have to pick a material that actually will produce more photons than it absorbs for a start, which kind of limits it down massively. And then from there, there's only a few of them. There'll only be a few different energies and therefore different light that you can actually emit. So you're stuck a little bit generally. I think you can tweak the wavelength ever so slightly, but you can't change it that much. So you're kind of limited a little bit by the materials that are actually able to laze. That will affect it.
And how do you decide which wavelength to use? Did I say that already? I asked that already. Yeah. So it's kind of whatever you get really at the end. There's a question about if you can make 100% reflective mirrors, and if you're not, what about the laser that escapes out the back of the mirror and things like that? Is that a risk? Is it dangerous?
Oh, that escapes out the back.
Leakage through the back of a mirror, I guess.
Leakage through the back, yeah. I think, especially at these lower powers, it should be okay. So you could put something, obviously these kind of lasers would be contained within a box, right? So I guess you could put something behind that 100% one to kind of absorb any light that does come out. And particularly for that kind of laser light, it's usually quite low power still. So even if it does strike something that comes out of the back of that 100% laser, 100% mirror, it won't be too high a power to cause any kind of significant damage to anything. But I suppose you could put something, you'd have it in a box, so it wouldn't just be kind of fleeing out into free space. You can put something in there to kind of block anything that would come out. But it should be, whether it's 100% or whether it's, 99.9999%, it's kind of, I guess in physics, we shouldn't really say anything's 100%, right? So 99.9999.
There's always a quantum correction.
There's always something that'll leak out. But you can, as I say, you can pop it in a box or put something to absorb it in the back. That it shouldn't cause any damage to anyone.
And I guess the high power lasers, we tend to not be in the room when it fires, and it tends to be a pulse system. So if you lock up the room, you fire the laser, and even if it was to leak out the back, there'd be no one around to notice it. So it's somewhat less dangerous. Although I have been in a laser lab where we've made some black marks on the wall. I should probably not. I'll leave that for a little bit. This is a chemistry question from Pauline's asking about how do you get the high temperature which you need to cause carbon dissociation? That's from a chemist on Neptune. How do you get the temperature high enough to cause carbons to dissociate? I don't know, is that... I
don't know about how the temperature gets high enough, because I guess it's the fact that you've got such a large planet, you're under high pressures, which kind of causes the temperatures to rise, essentially, but I don't know exactly kind of where the temperature would come from, if that makes sense. I think it's just related to the fact you're under high pressure, so the temperature kind of comes from that.
I think so too. Sort of rule of thumb is about a megabar hydrogen dissociates, and so chemistry breaks down above a megabar. Is a general rule of thumb.
That's a good. How do you know that? That's a good fact to know.
You see, actually, one of the experiments you showed, the Meinecke paper, that was one of my postdoc work. So
I saw a picture of the people on there, and I saw you sitting at the back, and I was like, I'll make sure I say this one right.
Hiding in the back of the photograph, yeah. So what do we have? How do you focus the laser beam? What sort of material can you use for such a high power laser? Was one of the questions. That was a nice one.
Yeah. So as I said, like during the amplifying kind of stage, you want to make your kind of beam as big as possible, and we don't mind if it gets a little bit bigger. It's not entirely focused, and there, as I say, it gets to diameters up to say 20 centimeters. So you won't focus it until right at the end. Now, the main problem with that kind of high fluence stuff is when it's actually passing through a material. So when it's passing through like a lens or an amplifier, that's when high fluence is a problem. But a reflecting optic will be fine. So you could use something called a focusing parabola that will focus it down, essentially acts kind of like a mirror to kind of bring it all in. So reflecting these high power lasers is fine. And won't actually damage it, but yeah, you wouldn't be able to like pass a lens or pass the light through a lens at the end, because the lens would definitely break at that kind of power and that kind of energy.
Excellent, thanks for that. We've got another question about now I'm going to paraphrase this question. If the questioner, if I'm misunderstanding the question, feel free to correct me. What's the benefit of using lasers than to use superconductors to compress lasers together? I think this is a fusion question, and I think you answered it during the talk after this question was posted. I think this is about whether you use lasers or magnets. And I think you mentioned they're kind of both alternatives. Is that fair? They're
both alternatives. I think in terms of the benefit, they're both just different ways of solving the same problem, right? So fusion achieved with a laser is something that you kind of do sharp, fast pulsed. Whereas magnetic confinement ones, you tend to use like a lower density, what we call a plasma, lower density fuel, and kind of keep it running for longer. It's just kind of two sides of the same coin in terms of trying to get the fuel to fuse. In terms of the benefits of using a laser-driven one, I mean, at the moment, the benefit is that we're getting quite a good amount of energy out with ICF compared to MCF, is what I would say. I think also from a kind of scientific point of view, it's quite nice to see that the research that goes into ICF can also be applicable to other places. You kind of have more flexible facilities almost. Like NIF does quite a lot of work in terms of obviously trying to achieve ICF, but you can also do research for other aspects of physics as well. So that can be quite interesting just from a scientist perspective, I would say. But yeah, it's kind of two ways of getting to the same end point, which way you pick.
Yeah. I wouldn't say one was, I think that's fair. I wouldn't say one was better than the other. I would say that if you've got two options, you've got two options and one of them might work, you probably best try both. I think that's probably the way I would phrase it. We're getting very close to it. I'm just going to rush through a few. One's about household applications. Could you power homes? And another, that's from Leventi, but Robbie's also asking, if you got more energy out than in, how would you use that energy to produce electricity? Yeah,
so the hope is that one day we'd be able to use it to power homes, so being able to connect it to the national grid would be the ideal scenario. So fusion is incredibly hard to achieve. So we probably, certainly, I can't see it happening in the near future in terms of being able to have kind of like mini reactors in our back garden. I don't think we're going to get quite to that stage, but we could certainly try and make kind of like larger facilities that would be able to produce lots and lots of power that we could then pump out to the grid and then power homes through that way. So that's kind of like the end goal, to be able to actually use it in place of kind of like oil and gas powered stuff. We could use a fusion reactor instead, which would be really, really cool. And then in terms of how you actually get the power out, this is still kind of like a work in progress in terms of how a fusion reactor itself would work. So at the moment, a lot of focus is on how we can actually just get fusion to happen. But then it's a completely different question in terms of how we can then translate that science into a reactor. One of the problems we have is that, you'd have to create lots and lots of these fusion events very quickly. How you get the energy out is something that we haven't quite decided yet. There's a few different ways you can do it, but it's something that we're still kind of trying to investigate in terms of scaling it up and how it's going to become something more usable.
Excellent. There's questions about how much energy is wasted making the direction of the lasers hit. I think that should be the Hall run, the obstacle before reaching the pellet. So do we lose energy in the laser by bouncing them off mirrors, I guess is the question.
Yeah, so I mean, in terms of actually being in the Hall run, I guess there'll be some energy loss in terms of like not all of the laser energy is going to be converted into X-rays that will again compress it. So you do have to take that into consideration in terms of how efficient your conversion to X-rays is. There are things that you can do to kind of increase it. So you can change the material of the Hall run slightly. You can change kind of like the gas that fills the canister a little bit, and see if that improves the efficiency a little bit. So you do lose a bit of energy, but I don't think it's a great contributor in terms of how much you lose. Like you do lose some, but it's not like you lose like 99% or anything. I don't think
I guess following up, what kind of gain do you get in that kind of an ICF reaction? Is it a factor of 2 or 3, or is it factors of hundreds, or if you get it to ignite?
Oh, if we get it to ignite, we can get it up to kind of, I'm not sure. Depends how much we get to ignite, I think, is the whole thing. How much we actually get to burn, how big our fuel capsule is. We want to play about with how big the capsule is, how much fuel there is there, how much energy you can actually get out, and how much more. But I'm sure it's like kind of order of 10. You can get a decent.
Yeah, you end up with tens or hundreds and tens or hundreds. So I guess the few percent loss in the laser is probably less important. I mean, laser efficiency, that's probably another talk for another day. And actually, we're down to the last minute or so of the session, which has gone absolutely flown in. I think that's partly because of how interesting the talk was. So what I will do is I'll round up there. There were a couple of questions that we didn't get to answer, and it was more to do with the pressures required in for fusion, which of course you get high density and high temperature, you get high pressure for free. And there's more things about lasers, but there's loads of talk. You can hear more things about lasers in some of these podcasts. Just to thank Emma again, the recording of this event will be on the Department of Physics YouTube channel, and a link will be sent to everybody who holds a ticket for this. Also, if you'd like to find out more about the MOOC, you can find it on the Future Learn Technologies. Thanks everybody for joining us at this webinar, and sorry we've had to rush the finish, but I hope you've all enjoyed it. And thank you again, Emma, and all the technical support who made this happen. Thanks so much, and we'll catch up with you all at the next session.